All right, now let's talk about secondary indexes. So we went over primary indexes before, where you index a table by whether it's some ID or user dot value, which is a uint64t. But what if you want more than one index on a table? Is that possible? What if you want to index something by name? Well, you can do that. You can create another index. And the way that you do that is just by defining it underneath the table here, like just how we defined our multi-index table, the balances table. We just add another line here, and I'll show you how to do that in a second. But there is one thing that I want to cover before we do that, and that is the fact that you cannot modify the structure of a table while there's data or data inside of it. I mean, technically you can, but you're going to destroy it. It's not going to work. You're gonna go to look at your table, and you're going to say, "Where'd all my data go? It's all the balances are gone. I've ruined everything." Don't be that guy. You can't do that. That's not how it works on EOS and Wax. You have to have an empty table if you're going to modify the structure of it. So typically what people do if you already have a table with information inside of it is they just create a second table, then copy all the information over to the second one, then empty out the first one, and then copy all the information back to the first one. That's typically how that's done, but we don't need to go through that whole process. So for the sake of this tutorial, let's just create another table called balances, and we'll just add like two S's here. Balances, and bals table. And then, all right, so now we have a new table. And in order for us to add a secondary index to that, you know how we would do that. Obviously, we would copy and paste like we always do. So right here at the end of this line, where it says using bals table, we're going to put a comma and then hit enter, create another line. And now what we're saying is this is also indexed by the user column. This is indexed by, no, you know what? That doesn't work that way. So we'll call this second column, we'll create another one called user name. So we have the user, which is going to be the primary key. That's going to be the dot value, because you have to have that primary key there no matter what. Now we'll create a secondary called user name, and we'll say this table is indexed by user name, and it is going to be the second key. I know this probably looks confusing, but second key, right? What does that mean? How do we have a second key? Well, that's easy. We just do that right here. So we're going to copy this first thing. We'll say second key equals second D key. No, that's not. Second key return username dot value. And what that's going to do is it allows us to have the username as an index, but when we call the function to index it, it's going to return us a uint64t. This is all happening behind the scenes. It doesn't really matter. The important part is that you're able to now index by username. Why would you want to do this? Well, because you might want to look, you might have a column that is, let's say, not unique. So, in this case, this actually doesn't really make much sense because the user is the primary key. So we're never going to have a unique username field. This wouldn't make a lot of sense unless we change the primary key to just be like some random number. Aside from the fact that we can actually just display the username, that might make it easy for some people to search the table. So that might be a use case here, but really it's pointless, right? This is more used for like if you're going to have a situation where that secondary one user might have multiple entries in the table. So they might have a primary key of 1 and a primary key of 3 and a primary key of 10. They have a bunch of different rows, but in that you want to be able to look, like, give me all the records of this one user. So that's where the secondary index comes into play. You'd now be able to search specifically for this user by secondary index. You know what? Let's change this original one to ID. ID. Let's just compile this one more time to make sure it's good. Okay, so I'm trying to think how I'm going to display this info to you. How about let's add another column to this table. We'll make it a uint64t, and we'll call it total records. It's going to be just the total amount of records that a specific user has. So let's create another action. We'll copy this add message thing. We'll call this add user record, add user rec. Yeah, we don't need anything besides the username really for this. And let's say require auth get self. So this way the contract is able to do this itself. We don't need a user to sign this. I'll show you why in a second. And then all we're going to do here is we're going to add this info into a table. So we'll do Bals table, user table within get self.value scope, and we'll do user table dot in place. We can't charge the user if we're the one signing this, so we'll put us as the RAM payer, and we'll do the ID is going to be just an available primary key just to make it unique each time. And row.username is going to be user. And row.total records, if we add the user, we're just going to call it 0. We don't even need to put that because that's what it would be. If you don't define it, it's just going to initialize it to this default, which would be 0. Row.total records. The same thing happens with an asset. So since we're not specifying what we want the balance to be here, it's just going to set that to be 0. And that's fine. So let's do this for now. You'll see where I'm going with this in a second. Compile it one more time. And while it's locked again, very annoying. All right, so the contract is now deployed, so there should be a new action on it. If we refresh, there should be a new table and a new action. So we have this new table here and this action called add user rec. So we'll call the user MikeDCrypto5. Missing a thought. I'm not logged in as code tutorial now. We did one. Let's submit it again, and we should get 2 unique records now because we're not modifying anything existing. Now we should have 3 unique records after this next one. So if we go back to the table, there we go. We've got 3 records. They each have a unique primary key, but the username is MikeDCrypto5 on all of them. So you've got a unique key, but you have a non-unique index. And now just so you can see that this actually works properly in a second, let's add like some other user called John Smith. So now there's 4 total entries in the table. All right, so now if we go back to our add user, you know what, let's create a new action. Called count records. And the name, we'll take in a name, we'll require auth of ourself, and we'll initialize the connection with this balances table here, the new balance table that has 3 records for MikeDCrypto5. And we just want to count these, right? And we'll put the input somewhere. So what we'll do is we'll store the input and we'll just choose one of these rows. We'll say row 2, ID 2. So we'll say, first let's make sure that ID 2 exists. It does right here, ID 2. So we'll say auto iterator equals user table dot find 2, and then we just want to check iterator is not equal to user table dot end. Row 2 was not found. I mean, you should understand what this means by now, so I don't really need to walk you through it, I guess. We've done this a few times. So after we run that check, we know that row 2 was found. What we're going to do now, and there's going to be more copy and pasting here again. In order for us to access this secondary index now, what we want to do is we want to make sure that we only look for records where the username is MikeDCrypto5, and that's it, nothing else. We don't want John Smith. We don't want to deal with it. We don't want John Smith taking up our CPU time, while we're doing our searching. We just want to pull the 3 records from MikeDCrypto5 and nothing else. So what we do is we define a secondary index now. Well, the secondary index is already defined, in the table, but we define it here now in our count records action. So we say auto user secondary equals get index username. All this means is that, hey, down here we've got a secondary index called username on this table. Let's get that right now and look through it. All right, so now we know what that secondary index is, but how do we actually choose only the MikeDCrypto5 pieces from it, right? We don't want the whole secondary index. That's everything. That's pointless. What's the point of doing that? So we have to define a lower bound and an upper bound. So more copy and pasting. What we do is the lower bound, we'll call this variable users low iterator equals the secondary index name, user secondary, dot lower bound, and then who do we want to look for? What's the value that we're searching for? Well, in this case, we're searching for MikeDCrypto5 dot value. All right, and we have to do the same thing now for the upper bound. So we can just copy this and say users up iterator equals users secondary upper bound. Same thing, MikeDCrypto5 dot value. What this did is it's basically just saying, hey, we want to only search. The lowest thing we want to search for is MikeDCrypto5, and the highest thing we want to search for is MikeDCrypto5. And anything outside of that range in this secondary index, that's not for us. We don't want that. So we're just going to get these 3 rows, and it's not going to take up any extra resources either. It's like automatically going to give us that without really costing us much CPU or anything. So what we can do now is, let's say we create a variable called int. It'll be an integer. We'll say found count equals 0. So far we found 0 records for MikeDCrypto5, and then we can say something like for auto found iterator equals users low iterator. If found iterator does not equal users up iterator, found iterator plus plus. Now I know this probably looks a bit confusing, but basically this probably isn't even the most efficient way to do this either. But basically what we're saying here is we're just going to loop through everything from the lower bound that we just defined and to the upper bound. And if we didn't make it all the way through yet, then just keep increasing by 1. And then we'll just say, for each one of these, each one will say found count plus plus, and this should increment the number by 1. So at the end of this, our found count should be 3. All right, and then once we're all done with this, we're just going to modify that original, the iterator where we looked for number 2. We're going to modify row number 2, and we're just going to change the total records number. This should end up as 3 when we're done. So we'll say user table. We'll say user table.modify. And remember, we have to specify which row we're modifying. So we'll say iterator, because we've defined that up here already. We're modifying the iterator. We're the RAM pair. And we're just going to change row.total records to equal found count. And that's it. So what this should do is get us all records from MikeDCrypto5, count each one of them, and then just change it in row number 2, which is pointless, right? I'm doing this to show you like how you can get a lower and upper bound and iterate through a secondary index. It's useful. It might not seem like it right now, but trust me. Let's compile this contract again. Oh, I made a mistake. It should be user table get index. User table, not users. User table dot get index username. That should work now. All right, now let's deploy this. It better not be locked. And that's been deployed. So now we can go back to the contract. We can see row number 2 still has a total records of 0. This should change to 3 after we do the count records for Mike Decrypto 5. Yeah, I should have just put user.value in here, but it doesn't matter. All right, this is something you're going to run into if you're updating your contracts constantly like I'm doing. This just means that gray mass or whatever API node that your wallet is using, it might not have the new ABI file yet. Sometimes they're a couple minutes behind. For instance, if we go to the account tab, you can see these transactions aren't even confirmed yet. They're still processing. So certain wallets, they might just take a couple of minutes to reflect new changes. So since our ABI file just changed to add some new action called count records, the wallet itself, when it tries to submit this transaction, it's like, I don't even see that. What is count records? I haven't seen that. So sometimes you just need to give it a couple of minutes, or maybe you change the node, but I'm just going to wait a couple of minutes and then come back to this. I'm actually just going to change the API inside of Anchor Wallet that I'm using for Wax Testnet. I'm going to change it to be the one that I actually submitted the transaction to, so maybe they'll have the ABI. Yep, looks good. I just need to sign back into my wallet again. All right, and now, yep, it changed to 3. The total records is 3. So I know that whole exercise was completely pointless, it seems like. This isn't typically what you're going to do with a lower bound and an upper bound. The point of that exercise was to basically show you how you can access a secondary index on a table, and basically counting it was just kind of to show you that it worked, I guess. So we did, in fact, get 3 records instead of 4 because John Smith is in this table as well, and we didn't get John Smith. We only got the index that we asked for. So I guess now might be a good time to talk a bit more about CPU and RAM costs. We've kind of gone over RAM for the most part. RAM is going to be actual data that you store in your table. It's temporary, so it's only there while you store it. And like, for instance, code tutorial is the RAM payer on all these rows in this table. Well, if one of these rows gets deleted, nobody needs to do anything. Code tutorial just automatically gets that RAM back. And the same thing goes if you charge the user for the RAM in your table. They pay while it's there, but if you ever delete that record, they automatically get their RAM back. You don't need to do anything at all. It just happens. It goes back to their account. So that's that for RAM. Now with CPU is more related to processing things. I mean, that's literally like in the name. But basically, for instance, we just iterated through these 3 usernames a minute ago, this secondary index, the 3 rows. And we went through each one of them, and all we did was increment a number, right? So that's not really much CPU, but imagine Mike Decrypto 5 had a ton of records in this table. Well, loading every single one of those rows and then iterating through each one of them to increment a number, that can get expensive CPU-wise over time because you're going through each row individually and doing a thing. So not only are you doing a thing so many times, but there's also something to be said for just loading the row in general. So let's put it like this. This data is nothing, right? We've got an ID, which is just a number, a name, a balance, total records. This is nothing, so it's really not much CPU at all. Like, from left to right, I'm talking about the different rows that are in this table. Now, imagine, though, you're actually handling some very complex data, right? You have, let's say, some NFT staking contract or something, and you have the asset IDs of, like, some user has, there are people with 5,000 NFTs staked on WaxDAO in a single farm. So imagine having every single one of those asset IDs stored in a vector in one of these rows. A vector just means a list, for those of you who don't know. So you might have a row that has 5,000 different asset IDs in it. Just to access that row, right? Like even if you're not doing anything with those 5,000 NFTs, just to access the row at all and load it into memory, that costs CPU. So let's say you were going through a table, Mike D Crypto 5. Let's say you wanted to go through these three rows right here, right? And in row number one, this one right here, let's say I had that list of 5,000 NFTs, and I did the same thing as before, where I start off at the lower bound of Mike D Crypto 5, and I iterate through to go all the way to the upper bound to all three rows. But let's say I'm checking for some condition, right? Like if ID equals 2, which would be pointless, but just go with it for a second. Humor me. If I did that, I'd only be trying to do something with row 2, which means I'd be loading row 1 into memory and all 5,000 of those asset IDs for no reason at all, and wasting however much CPU that is. Just loading it, even though I'm not doing anything with row 1, just loading it into memory as I iterate through and go past it, that costs a lot of CPU to load that whole row. So you have to be, very thoughtful and mindful about your design. There are trade-offs with RAM. There are trade-offs with CPU. For instance, a new index on a table costs, I believe, 112 bytes. I believe that's what it is for primary or for secondary. And that's just for the index itself, not for the data inside of it. So what that means is that each row that you create in a table, no matter what, it's going to cost you 112 bytes of RAM, bare minimum, even without any data stored. So let's say for that same situation, you have a list of 5,000 asset IDs. Maybe you're thinking, well, what if I only need to access one of those asset IDs? It wouldn't make sense to load that whole row, that whole 5,000, put all that into CPU just to do something with the one asset ID. That makes no sense. Why would I do that? That's a waste of CPU. That's what you would think, right? But then you run into you might think, all right, so how about I just create a table, and every time there's a new asset ID, I create a new row for it, so that I can just do a dot find. And this way I don't need to load all these. I just find the one I need and then do something with it. That would save a ton of CPU. Well, that is correct. It would save a ton of CPU by doing it that way. But the problem is, you then run into the issue that you're now paying 112 bytes of RAM for every single row that you create. 5,000 NFTs times 112 bytes, 600,000-ish, 560,000, whatever it is. So that's like, why would you do that? Whereas an asset ID is 8 bytes, so the 5,000 times 8 is 4,000. So, you'd be like 150xing your RAM cost just to save some CPU. That might have confused you, that whole example. But the point is, there are trade-offs whichever way you go. You have to keep RAM in mind when you design your data structure, but you also have to keep CPU in mind. There are complex ways to navigate the situation and workarounds that people create. There are people a lot smarter than me. I'm not the best at this stuff. My contracts probably aren't like as efficient as they can be. So I don't want to give you guys advice that's wrong, but I would highly suggest you just be very mindful about the way you design your data, and just try to optimize it for CPU and for RAM as best as you can, and just understand that there are trade-offs whichever way you go.